Alright, so we're continuing our discussion of numbers in chemistry, and we're going to talk right now about something called significant figures. So, have you ever noticed that when you put numbers into a calculator, a lot of times you'll get an answer that has a whole bunch of decimal places? And you may raise your hand and ask your teacher, hey, where am I supposed to round to? Where do you want me to round this? So what we're going to talk about is, since our calculator doesn't really know where we're supposed to round, there are some rules in chemistry, especially when we're talking about measured amounts. There are some rules about where we round our answers. So, first of all, remember we've been talking about numbers and quantitative measurements. So there's two kinds of numbers, exact numbers and measured numbers. So exact numbers are infinitely important. For example, as it says here, if I have 3 monkeys, I know for sure it's exactly 3. So anytime I'm counting, I'm certain that my answer there is a whole number exactly. But a measured number is always subject to what's called error. And we've already talked about calculating percent error and things like that. Any kind of a measuring device can have error. And it's only going to be as precise as good as the device is. For example, some balances only measure to the tenths place. Other digital balances will go to the thousandths place. They are a more precise balance. And if you needed to measure a tiny, tiny amount, you wouldn't be able to measure it on a balance that only goes to the tenths place. If I need exactly 0.211 grams of something, and my balance only goes to the tenths place, it would be impossible for me to get exactly 0.211. And the same is true with any measuring device. So measuring devices, because they have error, the calculator doesn't know that. And so our measurements, and therefore where we need to round, can only be as accurate as our worst measurement whenever we're calculating something. So let's go through this in a little more detail. So an exact number is, there are 2 ways we can have an exact number. One would be counting. If I have 2 soccer balls, you can be certain it's exactly 2 soccer balls, that it's not 2.5, 2.3, right? You're counting. This is a whole number. 2 soccer balls is the same as 2.0000000, exactly 2 soccer balls. 4 pizzas, same thing. An exact relationship are things like a foot is equal to 12 inches. 1 meter is 100 centimeters. We know that those are exact. We're not talking about something where I'm going and I'm measuring this. Measured things, again, require an instrument. So, for example, 1 yard is equal to 3 feet. This would be an exact number. A yard is exactly 3 feet. 3.000000000 feet. Look at our second one. The diameter of a red blood cell is 6 times 10 to the negative 4th centimeters. This is not an exact value. This is a measured value, because I would have needed a tool, some kind of very tiny ruler under a microscope or something like that, to measure the diameter of a red blood cell. There are 6 hats. This would be an exact number. Why? Because it's a counting number, right? So conversion factors and counting are our 2 scenarios where we don't have to worry about where to round. Those are exact numbers. Our last one, gold melts at 1064 degrees Celsius. This is a measured number. If I had a better thermometer, maybe I would know that it's 1064.2 degrees Celsius. Or maybe if I had an even better one, it's 1064.2713 degrees Celsius. So depending on how precise my measuring tool is, I can get more and more specific or precise with my answer. Alright, so when I'm using a measuring tool, there's a rule here. When you are using a measuring tool, you are always going to measure 1 digit beyond the scale that is given. For example, let's take a look at this graduated cylinder. So I know in this graduated cylinder that the level of the water, and you're supposed to measure where it dips, that's called the meniscus. So I can clearly see markings for the ones place, right? This is 16, this is 17, this is 18, this is 19. I cannot see markings for the tenths place, the 0.1. So I have the ability, the rule is that I am allowed to estimate to the tenths place. So if my scale goes to the ones, I estimate to the tenths. So I can see that it's somewhere between 17 and 18. So I might say 17.4. Always use my units, milliliters. 17.5 milliliters. Maybe I think it's a little more, 17.6 milliliters. None of these are wrong because the last digit in any measurement is your estimated digit. It's the digit that you're not positive about because you can't physically see a scale for that digit. All right? So in this case, as I said, you can see it's between 17 and 18. Maybe you think it is 17.4, 17.5, but you're guessing at the tenths place. Now where this throws people off, everybody usually understands this. Where people get confused here is when it's right on the line. So let me erase my work. So let's say that it was right here and you thought it was exactly dipping on the line. Then what ends up happening is I get people that say, well, it's right on the line, so it's 17. It's not 17. I still have to estimate to the tenths place because my scale goes to the ones place. So if I think it's exactly 17, I'm going to say 17.0 milliliters. That tells the person reading my measurement that my scale went to the ones and my estimation of the tenths is 0.0. So you must estimate one digit beyond the scale. So let's look at this scale. So this scale goes, remember my last scale went to the ones place. Look at this scale. This scale goes to the tenths place. 1.1, 1.2, 0.3, 0.4, 0.5, 0.6, 0.7. Since my scale goes to the tenths, I have to estimate one digit further. So I have to go to the hundredths. I must estimate to the hundredths. Even if my line was right on the 0.6, even if I thought the measurement was 1.6, I need to say, if I think it's right on that, 1.60. 1.6 and 1.60 don't mean the same thing when you're measuring. In other words, imagine there were no lines here at all. All I could see was 1, 2, 3. Then I could estimate 1.6 or 1.7 because I would be estimating the tenths place because my scale, if I only had these numbers and everything was blank in between, I wouldn't know the tenths, so I'd be estimating the tenths. But since I know the tenths, I have to estimate to the hundredths. In this case, we might think 1.67 centimeters, of course, are units, right? We always are going to estimate one digit beyond the scale, and we stop at that last digit, which is our best guess. Another person might estimate something slightly different. We're not certain about this one. These are our certain digits, and then this last one is my estimated digit. It's important in the number. I'm fairly certain, but it's still a guess. All right? If we look at a couple more examples, the length of the stick, this goes to tenths, so I need to go to hundredths. So my correct answer, 4.54, or maybe you would have thought if it wasn't multiple choice, 4.53, 4.55, but you definitely would have needed to go to the hundredths place. Here's another one. This one also goes to, let's see, this goes to the tenths. So again, you would need to estimate to the hundredths place, right? Right here. 8.00. Even though you think it's right on the 8, you still need to go to the hundredths. This tells me my scale went to the tenths and I guessed the hundredths. If my scale only had, the single digits and no lines in between, that's when I would estimate 8.0. So again, in numbers, all but one of the significant digits are the ones we know with certainty. And then our last one, remember, is our estimated digit. This will indicate the precision of our measurements. You're going to include all the digits you know plus the estimated digits. You always report your answer one digit beyond the scale, and then the reader knows that you were certain about everything except the last one, and the last one is your estimated digit. And you can see here, they're just showing you an example. So in this one, I basically guessed on the 0.07. I know these three, and my best guess is that it's between 54.06 and 54.08. Now, if I look at this measurement, I must have had a really good balance, right? Because this balance, I could estimate all the way to the 0.00001. So I have a much better balance. I have a much better measuring instrument, and that allowed me to get more precision. In other words, go more decimal places in my answer. And even in a digital balance, by the way, if this was the reading on a digital balance, the digital balance, you'll notice, will usually have something off to the side that says measurements are plus or minus blah, 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 blah. That's basically them telling you the same thing, that the balance digitally is estimating that last digit, that it can't guarantee that that one is correct. It should be close, but it's still an estimate. All right, we also have some rules. So once we make our measurements about zeros, because even if I measure and I only want to measure, say, to the tens place, I can't just take a number, and if I'm estimating, say, that my estimate is 270, I can't just get rid of this zero. It's a placeholder. It needs to stay. And I also need zeros in a number like this. These zeros, you can't just get rid of them. I can't just say, oh, well, these weren't really part of my measurement, so I'm going to change my number to 0.23. That has a completely different meaning. So we need to know, for chemistry, when should zeros count? When are they actually part of your measurement? And when are they considered just placeholders and not significant digits? So here are the rules. First of all, any zeros in the middle of a number always count. They're always significant. So this 0 is part of my measurement. This number has 5 significant digits. This would be my estimated, and then these would be my exact. Rule 2, zeros at the beginning of a number are not significant. They are placeholders. So in this number, only these 3 are part of my actual measurement. And this one, just these 4. The zeros in the front, we have to have them, but they're not actually part of my measurement. In fact, if you changed this to scientific notation, you wouldn't write the zeros. This would be 8.34 times 10 to the negative 2. Notice the zeros would go away. And the same thing with this other measurement. So these zeros are really to help me see the value of my number, but my actual measurement are these 3. These are the 3 that we would call significant figures. Zeros at the end of a number after a decimal point are significant. So when I see this number 138.200, this 0 is part of my measurement. This is my estimated digit. So this number, 138.2, even though mathematically it has the same value as 138.200, this would mean I used a much more precise scale, this one, because my estimated digit is this last 0. Here I was only able to estimate to the tenths place. Or I guess this would be a ruler, actually. It's the length. And then rule 4, zeros at the end of a number before an implied decimal, meaning if there's no decimal in the number, again, they are not considered significant. So the number 3000 only has 1 significant digit. This is my estimated digit, and these zeros are placeholders. If I was going to turn this number into scientific notation, it would be 3 times 10 to the third. But if I add a decimal point, now it would be 3.000 times 10 to the third. Notice the difference. One has more significant digits than the other. One, I used a much better measuring tool than the other. So here are some. You can pause it if you want to. We did these in class. First one, all the digits are significant. Anything that's not a 0 is significant. The second one, 3. These are significant. These are not. 5. These are not significant. They're at the beginning of a number. All of these are, including zeros at the end. This one, 5. All are significant. This one, only 2, because without the decimal point, these are placeholders. If I changed this to scientific notation, it would just be 4.8 times 10 to the fourth. Whereas this one would have to be written 4.8000 times 10 to the fourth. Everything here, everything that's written in scientific notation, the whole base number is significant. And then this last one, everything, because these zeros are between non-zero numbers, and this one, there's a decimal.